All right, let's just dive right in. Welcome to this explainer. Today, we're looking at what might literally be the ultimate detective tool for your data, the control chart. Whether you're running a massive manufacturing plant, managing a global IT network, or just trying to optimize a financial portfolio, finding that true signal hidden inside all the daily operational noise is absolutely crucial. So we're going to unpack exactly how this incredibly powerful tool lets you do just that. Here's our roadmap for today. We're going to start with the problem of variation, enter the control chart itself, learn about reading those signals, dive into a real-world case study with Sujal Dairy, and finally look at applications way beyond the factory floor. Section 1. The problem of variation. Let's start with a universal challenge that pretty much every single industry on the planet has to deal with. When you're staring down a flawed process, you really have to ask this one fundamental question before you can even think about fixing it. What's going wrong? Identifying variants or defects, well, that's the bedrock of quality management, right? I mean, no products or services can be produced in mass quantities exactly the same every single time. There's always going to be some variation in manpower, machines, materials, or just the environment. But before we can actually find that root cause, we have to definitively identify that a variance actually exists in the first place. And this brings us to an incredibly bold, historic claim. Dr. Karu Ishiwaka, who is a total legend in quality management, famously claimed that a whopping 95% of workplace problems could be solved using just 7 basic quality control tools. He truly believed that if these fundamental quantitative instruments were understood across an entire company, these massive, complex problems would honestly just dissolve. Which brings us to part 2. Enter the control chart. Let's see how we can use this one specific tool out of those 7 to actually visualize and tackle those problems. So, developed by Walter A. Shewart way back in the 1920s at Bell Telephone Laboratories, the control chart, which, by the way, is sometimes called the Shewart chart, is basically the definitive graphical device to monitor stability and flag any weird abnormalities. It's especially valuable because it evaluates time-bound data. Whether we're talking about production quality, customer service response times, or delivery accuracy, comparing your current data to historical control limits lets you know definitively if a process is predictable or if it has completely gone off the rails. This cleanly breaks down the simple anatomy of the tool. Every single control chart has a centerline, usually just the mean or average of your historical data. Then it has an upper control limit and a lower control limit. Now, these are often called natural process limits, and they're typically set at exactly 3 standard deviations away from that center line. These limits establish the exact mathematical threshold where a process output goes from just being normal, everyday variation to being statistically unlikely, basically an anomaly. Part 3. Reading the signals. So, how do we actually use this anatomy to decode what the data is trying to tell us? The absolute most crucial point here is understanding a specific binary. You really have to filter out the normal, everyday noise to find the actionable signals. First, we've got common cause variation. This is inherent noise. It's consistent, it's predictable, and honestly, you can't really get rid of it unless you completely redesign your entire system. Then, on the other hand, you have special cause variation. These are the unpredictable signals that scream, hey, something specific is genuinely broken here and needs to be fixed right now. Think of a data point resting safely within our upper and lower boundaries. We'll call it point A. That represents common cause variation. It's just part of the daily noise, no big deal. But then imagine another point, point B, that violently breaches that upper control limit. That point is literally screaming that a special cause variation just happened. When your data hits a point like that, it's your definitive signal to stop the line, gather your team, and figure out what went wrong.
All right, part 4, case study on Sujal Dairy. Let's look at a real-world application to see how this translates into tangible problem solving.
Grounding our data collection with the 5 Ws makes the whole setup incredibly clear before we even touch the math. This is a real, actual study from Sujal Dairy in Kathmandu, Nepal. The team there wanted to monitor the weight of packaged pasteurized milk pouches, and they were aiming for a strict target of 513 grams. They sampled the production line at exact 57-minute intervals to build out their data set. When comparing the performance of 2 different packaging machines running the exact same operation, a stark contrast immediately jumps out. For the solid non-fats metric, which is essentially the nutritional components of the milk minus the fat, both machines were perfectly under control. But for weight variation, Machine 2 was totally stable, while Machine 1 had a massive critical issue.
It was entirely out of statistical control.
And mapping this out on an X-bar control chart, which just tracks the average weight over time, provides the absolute smoking gun for machine 1. Imagine a center mean line bordered by upper and lower control limits. Now picture the data line violently spiking above that top limit and then plunging way below the bottom limit. This wasn't just a machine running slightly heavy. This was a process experiencing wild, totally unpredictable special cause variation.
But because the control chart flagged the exact moments of failure, the team didn't have to just guess. They used other tools, like a fishbone diagram, to investigate the specific timestamps of those massive spikes. And the result? Well, they found that one specific filling nozzle on machine 1 was malfunctioning. They repaired the nozzle, brought the process back under control, and eliminated a ton of waste. Literally finding the signal in the noise saved the company significant money.
Part 5, Beyond the Factory Floor. Let's look at this tool in a modern context, because you might be thinking this is only for manufacturing physical products. So remember Dr. Ishikawa's claim that these tools solve 95% of problems? Well, a massive University of Galway study of over 400 global quality professionals across 5 continents revealed a very different modern reality. Today, less than 25% of professionals actually believe that claim. Why is that? Mostly because modern business issues often stem from highly complex organizational architecture and massive information flow failures, rather than just, physical widgets breaking on an assembly line. But the big takeaway here is the massive missed opportunity. That Galway study found that control charts are vastly underutilized outside of production environments. They are the absolute least applied tools in IT and finance functions. Yet, these sectors deal with massive amounts of time-bound data. Think about server downtime, financial transaction errors, or customer service response times. These are all critical processes that absolutely can and should be tracked for special cause variation. There is a staggering statistic that highlights the real barrier to entry here. 40% of global professionals, and actually up to 62% in South America, admit they don't apply these tools correctly on the first try. The issue isn't the underlying math, it's a lack of proper training. People are just focusing on clicking software buttons rather than truly understanding the fundamental purpose of the tool, or maybe they just lack the management support to consistently gather accurate data. So whether you're manufacturing milk pouches in Kathmandu or managing a giant IT server farm in Silicon Valley, data without analysis is honestly just noise. The control chart is a simple, highly visual way to stop guessing and start knowing for sure. I'll leave you with this thought to consider for your own operations. What invisible problems could a control chart expose in your industry today? Thanks so much for joining me on this explainer.